Welcome everybody to this lecture series on anaerobic sewage treatment. It's my pleasure to introduce you the topic today. And we will start with a general background on anaerobic digestion for domestic sewage treatment. What we do in this lecture is that we dive into anaerobic digestion and wastewater treatment with the following learning objectives. With this lecture series, we would like to try to understand the principles of anaerobic wastewater treatment and to do some energy calculations linked to anaerobic treatment. We will make a COD balance over an anaerobic reactor, and we will discuss the types of anaerobic reactors that are currently applied. We will focus on USB reactor design, and then we will give some examples of centralized anaerobic sewage treatment and some decentralized anaerobic treatment applications. Now, the content of this lecture series is well described in the book chapters, Biological Wastewater Treatment, of which the first release was in 2008 and the second release in 2020 with our colleagues. And the chapter on anaerobic treatment is chapter 16 in the booklet. Now first, to get introduced to this topic, we have to realize what is anaerobic digestion, what is anaerobic treatment, what are we talking about? Well, we stabilize organic matter without the presence of oxygen, meaning the process is a reductive conversion process. We are mineralizing organic compounds to its mineralized end products. That means we have a solubilization of organically bound chemicals like ammonium, phosphate, sulfides. The fact that we do not need aeration means that we are talking about plain system for wastewater treatment. And there's no fossil fuel requirement. Moreover, as we will see, if you stabilize it anaerobically, we have bioenergy conversion. So the organic matter is transformed into methane gas, into biogas. And maybe there are other advantages that we'll come across during this lecture series. Of course, this is known already for years, and it is also applied widely in the commonly applied aerobic sewage treatment. If you quickly look to what happens in aerobic sewage treatment, and you see there an all wastewater treatment plant of the city of Amsterdam, we have an aerobic reactor in which we have an input of COD, and we need about 50 to 100 kilowatt hour of aeration to convert the 100 kilogram COD coming in. Now in the activated sludge plant, this waste, this COD, is converted into its mineralized end products. And in the meantime, sludge is growing. In fact, about 50% of the incoming COD is converted into sludge, newly grown aerobic sludge. The process is quite efficient, and in the effluent we have only 2 to 10 kilogram COD, meaning up to 98% process efficiency. Now, there's a lot of energy being released during this conversion, and that energy in part is going to the sludge, and the rest of the energy is lost as heat. It should be realized that not all the organic matter that is inside the sludge that we produced can be converted to methane, because that is what's happening in the activated sludge plant. The sludge that is being produced under aerobic conditions is converted using anaerobic digestion in methane gas. And you can balance, there's quite a lot of energy in the sludge that could compensate, in fact, completely for the energy demand. But as mentioned, not all the COD is converted into biogas. Moreover, there's also a low energy conversion efficiency from biogas to electricity. 30% for a biogas motor, maybe 40% for a combined heat power plant. Now the first question, if we work with anaerobic technology, we would like to know how much energy is stored biochemically. Now to calculate that, we have to oxidize the methane back to CO2 and water. In this equation, you have an oxidation of methane, CH4, with 2 moles of oxygen, giving CO2 and water. That means 1 mole of methane is equivalent to 2 moles of oxygen. Under normal standard temperature and pressure, 1 mole is equivalent to 22.4 liters of methane, which is then equivalent to 64 grams of oxygen. And 1 mole weighs 32, so 2 moles weigh 64 grams. Now this oxygen is also termed COD. It's an oxygen demand to oxidize the methane to CO2 and water. And that means that 1 liter of methane is equivalent to 2.86 grams of COD. Or vice versa, 1 gram of COD is equivalent to 0.35 liters of methane in the standard temperature and pressure. That means 0 degrees Celsius and 1 atmosphere. Now if you then look to the handbook of physics and we see what is now the energy content of this cubic meter of methane that we're going to produce, then you can see, and we focus on the central column in which megajoule per cubic meter is expressed, we see that natural gas is equivalent to 35.35 megajoule per cube. Pure dry methane gas is a little bit higher, and biogas methane is also 35.5. Now the difference between pure gas, dry gas methane and biogas methane is the content of water which is inside the biogas. Now if we use the biogas for heating, then that water will condensate and it will also evaporate, and that takes a little bit away of the energy that is available. We call it a higher heating value and a lower heating value. Now if we work with the energy content in anaerobic digestion, where we use the biogas methane, then we always work with the low heating value. Now if you combine now the COD with the energy content, then we can calculate that based on a higher heating value, 1 kilogram of COD is equivalent to 30.8 megajoule. Or in terms of low heating value, 1 kilogram of COD is equivalent to 12.4 megajoule. Now let's further compare aerobic and anaerobic treatment to get a clue what is now the big difference between these two. First, the aerobic conversion. As mentioned, under aerobic conditions, activated sludge, we stabilize organic matter with oxygen to CO2, water and the mineralized end products. Now in this reaction, the organic matter is the electron donor. And in fact, the oxygen is the electron acceptor. So the carbon gets oxidized and the oxygen gets reduced. And we see here the electron transport that is in fact occurring during these aerobic conversions. Now compare this with the anaerobic reaction. There is no oxygen demand, but water is the reactant. And in fact, the organic matter is both the electron donor and electron acceptor. And the water molecules, they deliver the oxygen. The end product of this reaction is the most oxidized form of carbon, which is CO2, and the most reduced form of carbon, which is methane. And this mixture, CO2 and methane, we call biogas. Now, if the organic compound is known, so the division between carbon, hydrogen, oxygen, nitrogen are known, we can in fact calculate how much oxygen is required to arrive to CO2, water and ammonium. Now, this exact calculation of oxygen is also called the COD calculation, the theoretical COD calculation of a known compound. We will come back later to that during this lecture. And if the compound is known, based on the similar principles, you can also calculate how much CO2 and how much methane we will produce during anaerobic conditions. And also that will be explained in some later slides. Now back to the comparison. Now let's take a very simple example as glucose. What happens now with glucose under aerobic conditions or under anaerobic conditions? Now first, the reaction itself. We see here a complete oxidation under aerobic conditions to CO2 and water, And under anaerobic conditions, we will get CO2 and methane. Now the second line, you see the energy release, and there's a big difference. We see about minus 3000 kilojoule per mole glucose under aerobic conditions and minus 400 kilojoule per mole glucose under anaerobic conditions, and that's a big difference. Apparently there's much more energy released during aerobic conversion in comparison to anaerobic conversion. And there's also a reason why aerobic bacteria, they grow very fast, and anaerobic bacteria grow very slowly. Now if you then realize that this conversion under anaerobic conditions is one of the most energetic conversions, you can also realize why it takes so long before the bacteria double. So why is the growth rate so low of anaerobic bacteria? The third line is the carbon balance. We see here that 50% of the carbon goes to CO2 and 50% of the carbon of glucose goes to the biomass, the newly grown bacteria. And that's completely different than the anaerobic conditions. 95% of the carbon goes to methane and CO2, also called biogas, and only 5% of the carbon goes to the biomass, which is about 10 times less. If you then compare the energy balances, we can calculate that about 60% of the energy content goes to the biomass and 40% of the energy content of the biochemical energy content of the compound is lost in heat production. And that is different in anaerobic conditions where 90% of the biochemical energy content is retained in the end product methane. And 5% of the energy content goes to biomass and only 5% is lost as heat. Resulting very fast growing of biomass under aerobic conditions, resulting in a sewage sludge problem. And we have a slow growth of biomass under anaerobic conditions. That means a long startup time of an anaerobic reactor. Now and then, of course, for the electromechanical equipment, it is important to realize that we do need energy input for aeration and aeration equipment, and this is of course absent for the anaerobic reactor systems. Comparing this, if we now directly go for anaerobic treatment, apparently we do not lose any biochemical energy content of the organic compounds. In fact, all the energy is retained. We enter an anaerobic reactor with 100 kilograms COD. We do not need aeration energy. We see that as little sludge is being produced. Most of the energy is contained in the biogas as methane. And we see that the effluent has a little bit more COD in the effluent, meaning the anaerobic reactors are apparently a little bit less efficient in their conversion than the aerobic counterparts. On the right hand you see a picture of such an application in Brazil, in Piracicaba, where in the top right you see the anaerobic reactor systems, and on the left side you see an aerated lagoon. So in principle you generate the energy to drive the aerated lagoons with the energy that you produced in the anaerobic reactors. Now you also see that this is a hill slope. Apparently there's a gravity division of the liquid, of the influent, and that means there is no energy required at all to operate this treatment plant. Now in terms of energy, the energy content of the organic matter is about 12.4 megajoule per kilogram COD. It's the lower heating value. And you save in aeration 3.6 megajoule per kilogram COD removed. So if the COD is fully converted to methane, the maximum energy savings in the systems is 16 megajoule per kilogram COD or 4.4 kilowatt hour per kilogram COD. So that's a real energy producing wastewater treatment plant. Now, there's some differences between anaerobic and aerobic conversion in relation to the microbial organisms that are performing the reactions. Aerobic organisms are very versatile, but the anaerobic conversion of organic matter follows certain steps. In fact, with sewage, and 50% of the sewage are suspended solids, the anaerobic system needs first to chop these big chunks of solids into small pieces to solubilize the suspended matter into solubilized organic matter. And we call that hydrolysis. And during hydrolysis, organic polymers, proteins, carbohydrates, lipids, they are in fact hydrolyzed into monomers and oligomers. Think about the amino acids, sugars and fatty acids as end products of hydrolysis. Now these end products are then subsequently used in the next step, which is called acidogenesis, which is a fermentation step. And in a fermentation step, water is used and we get an acid out of a neutral compound. And during acidogenesis, during the fermentation steps, we produce volatile fatty acids as end product, but also lactate and ethanol. Now there are other compounds, acetate and hydrogen COD, that are concomitantly produced. Now the next step is that these intermediate products are then taken up by acetogenic bacteria, which is a different group of bacteria. And they use these intermediates to transform them into hydrogen CO2 and acetate. And you now see that starting from the complex organic matter, we have very simple intermediate compounds at the end, consisting of hydrogen CO2 and acetate, before they are finally transformed into methane gas. Now the last step is a very typical step. It is performed not by bacteria, but by archaea, one of the oldest organisms of our planet. And they transform these intermediate products, hydrogen CO2 and acetate, into methane and CO2. It's a stepwise approach, and it is completely different in comparisons to the activated sludge conversions. Now let's first have a quick look to each of these steps. We will not go in all details. I'm afraid we don't have time in this course, but we will highlight the most important characteristics of each steps, which you should consider if you want to consider anaerobic treatment technology for the treatment of your sewage. Now first, hydrolysis. As I mentioned, this is a slow process because the bacteria have to chop the suspended solids into small pieces, and in fact it's a first order reaction rate that can be described by dsdt is minus kH, which is the hydrolysis coefficient, times the substrate concentration. The optimum pH of this process is 6. And now, since all the suspended solids needs to be solubilized, the retention time and particle size are determining parameters. Cellulose and hemicellulose degradation depends on the lignin fraction. So if we have a waste with a considerable fraction of lignin, and the cellulose is encrusted by the lignin, then hydrolysis takes more time. Now, since reactions are also temperature dependent, we have to realize that hydrolysis is very dependent on the temperature of the process. The temperature impacts the conversion processes, but also temperature impacts the solubility. Remember that fats, for instance, under low temperature conditions are hardly soluble. Try to wash your hands when you have butter on your hands. This will not be possible with cold water. So you need hot water to solubilize the fats. And we have the same problem if we treat very low temperature sewage. That will be problematic for anaerobic conditions. Now then finally, we may find some product inhibition by intermediates. And in the literature, compounds are mentioned like long chain fatty acids or LCFAs, ammonium, amino acids and hydrogen. The next step after hydrolysis was acidogenesis, fermentation. Example, here's a fermentation of sugars. Very important to understand that during the anaerobic conversion of sugars, we have a release of protons. This release of protons means that we make acids. And that is also very important. A neutralized compound, like a sugar, is converted into an acid. So, apparently, pH may. Since water is used and the oxygen of water is used, hydrogen is produced as a concomitant byproduct. In fact, this hydrogen formation is very typically for fermentation reactions. Now and then, fermentation is performed by a very large group of bacteria. About 1% of all bacteria are facultative fermenters. And I'm sure that you realize that if you look to your own kitchen, where you throw green waste in the bin. And in summertime, if you wait with your emptying your bin for 1 week, you will have this very strong smell. And maybe also you see some water appearing in your green waste. Now that is the first step, that is hydrolysis combined with fermentation. And also occurs at a low temperature. If you forget your milk in the fridge and you leave it for 1-2 weeks and try to drink it, it tastes acid. And this acid is exactly the reaction which is described here. Neutral sugars are converted into acid and your milk is not drinkable again. The first steps of anaerobic digestion. What you can also see in these two reactions, what is anaerobically oxidized here, is sucrose, C12H22O11. In the top reaction, you see that only acetate is being produced. But in the second reaction, you have also butyrate being produced. But you also see that you produce more hydrogen and more protons in the top reaction and less hydrogen in the second reaction. What does that mean? Well, if you now focus first on the top reaction, you see that sucrose is a neutral compound. It is fermented to acids, and you produce quite a high amount of hydrogen. If this hydrogen is now accumulating, then on a certain moment, you will get product inhibition. There's too much hydrogen, and the production of hydrogen does not give the bacteria energy enough. Now then the bacteria start to switch their metabolism. And instead of producing hydrogen, they are producing more reduced end products. Butyrate is more reduced than acetate. So by producing butyrate, they produce less hydrogen, and then the reaction will proceed. And that is also typically. So the end product depends on circumstances. More reduced products like ethanol, lactate, propionate, butyrate, CO2 and hydrogen you find in a two-step system where you first have an acidification reactor and secondly a methanogenic reactor. If you combine these two steps and you go immediately from the sugars to the acids, a one-step system, then you predominantly produce acetate, hydrogen and CO2 as the intermediate product. Also important to understand is that the production of acid proceeds up to pH 4, and then you will get product inhibition. But that means this pH optimum of these fermenters is wider than the pH optimum of the methanogens. And that means that your reactor can really acidify and the methanogens can be killed if the fermentation reaction takes the overhand. Now, I hope this explains the difference that a reactor condition will bring to the reaction that is performed by the biology inside the system. Now we talked about the sugars. Another important compound are proteins. And the proteins, which is a chain of amino acids, peptides, they are generally first hydrolyzed, and then later on these peptides are converted to their amino acids, and the amino acids are then both converted to the mineralized end products. Very typically for this reaction is a so-called Stickland reaction, where part of the amino acids are oxidized, and an anaerobic oxidation means usage of water and production of hydrogen, and the other part of the amino acids are reduced. Now in this example, alanine is oxidized. You see acetate and ammonium appearing, and glycine is reduced, accepting the hydrogen producing acetate and ammonium. And the combined reaction, alanine and glycine, you see a mineralization to acetate and ammonium and bicarbonate. Now there were the proteins. The last one are the fats and the long-chain fatty acids. And that is a real slow process. The anaerobic degradation of long-chain fatty acids proceeds via beta oxidation. What is beta oxidation? Well, The name itself, beta oxidation, means that the bacteria split two carbon atoms, and at the beta side, that carbon atom is being oxidized. So what you see here is a split off of acetate moieties. They are converted to acetate, and in the end, it depends. If you have an even chain of long chain fatty acids, you only get acetate, but with an uneven numbers of carbon atoms, you also get propionate as an end product. Now, what you need to know if you treat sewage is that this reaction is really a difficult reaction. That means if there's a lot of fats, then I'm sure that these fats may accumulate in your system, particularly if the temperature is low. Now, in addition to the saturated long-chain fatty acids and fats, we also have unsaturated LCFAs. Now, they have a double bond, and they first need to be hydrogenated before they can be degraded. For instance, oleate will be first converted before it's being degraded. Right, it's getting more difficult and more difficult. And now we arrive to, in fact, the most difficult step of the entire anaerobic conversion process. That's called acetate formation or acetogenesis. Here the fermentation products, they are converted into acetic acid, CO2 and hydrogen. And if you look to these reactions, which are very common reactions of very simple compounds, in fact, propionate, butyrate, ethanol, so they are very simple compounds. They are fermented to acetate plus the hydrogen. And what you also see, that the Gibbs free energy change of these reactions is positive. That means, under standard conditions, where you have equimolar amount of substrates and reactants, this reaction does not occur at all. And the positive delta G, a positive energy change, it doesn't occur. So you need to put energy in. However, this reaction can only proceed if the hydrogen that is being produced is taken away effectively by a hydrogen consumer. And under anaerobic conditions, the most important hydrogen consumer are the methanogens, because they take away the hydrogen plus the CO2, converting it to methane. And if these organisms are very efficient, then the concentration of hydrogen in the acetogenic reactions is going to very low levels and bringing the delta energy change to negative values. Because what you can see here, hydrogen CO2 has a very negative energy change, about minus 140 kilojoule per mole. So apparently, and that is also very typical for anaerobic conditions, you need a syntrophic association between a hydrogen producer and a hydrogen consumer, an acetogen and a methanogen. Now, if you would like to calculate yourself, this is the Gibbs free energy change that is used in these calculations. And what is important to realize is, if you look to these equations, is that the amount of reactants that we produce is the power in this equation. So the delta G, the Gibbs free energy change, is in fact the standard Gibbs free energy change plus R times T times ln. The products to the power of the amount of moles that are being produced divided by the substrates to the power of the amount of moles of substrate being used. And if you do remember, propionate oxidation delivered 3 moles of hydrogen. And that's why, if we accumulate hydrogen, propionate oxidation is one of the first VFAs that will be retarded in the conversion. The presence of propionate in the effluent of an anaerobic reactor is therefore a sign that something, the balance is not completely alright between the acetogenic bacteria and the methanogenic bacteria. If we bring this to a graph, and this looks like a very complex graph, I will explain it. Well, first the x-axis, we see the hydrogen partial pressure in the biogas. It is given as a minus log pH2, partial pressure value. That means if we have a value of 2 minus log pH, that means a very high pressure. If the value is 8, 10 to the power minus 8, it's a very low pressure. So in this graph, at the axis, at the left-hand side of the axis, is a very high pressure, and at the right-hand side is a very low pressure. Now, then you see a dotted line, and that's a dotted line is where we have an energy change of 0. When the energy change is positive, and which is the bottom part of the y-axis, then the reaction will not occur. However, when the delta energy change is negative, and it is above the dotted line on the y-axis, then the reaction will occur. Now let us view to the methanogenic and the acetogenic reactions how they look like. For the hydrogen and CO2 conversion to methane. The very high partial presence of hydrogen, there's a lot of hydrogen present, then the bacteria can get a lot of energy out of this reaction. And we see a value of above minus 100, minus 137 if you do remember. However, if the hydrogen partial pressure is dropping, so there is less presence of hydrogen, the bacteria can less and less energy out of this reaction. And at a certain moment, about 10 to the power minus 6 bar of atmosphere of hydrogen partial pressure, the reaction will not occur anymore. Now we will look next to this hydrogen to methane conversion to the propionate conversion. And this is a reversed. Propionate plus 3 water gives acetate, bicarbonate, a proton, and 3 hydrogen molecules. When the partial pressure of hydrogen is very high, this reaction will not occur. That's why the delta G is positive at the bottom part of the y-axis. However, if we take away the hydrogen very effectively, then we come to a negative value of the delta energy change. And then the reaction can occur. So at a certain moment, and that's about at the time 10 minus 3, 10 minus 4, the delta G becomes negative and the reaction will occur. And the same is true for butyrate. And you can do that with other compounds as well. What you see here occurring is a triangle. And this triangle is called the methanogenic niche, in which the complete conversion of organic compounds to methane can occur between a border of the hydrogen partial pressure in the anaerobic reactors, which is more or less between the 10 to the power minus 3 minus 4 up to the 10 to the power minus 6. And that is the normal hydrogen partial pressure in an anaerobic bioreactor. Finally, will occur at the methanogenesis stage. Here you see all the reactions that can occur under methanogenic conditions deriving to methane. So the most prominent reactions are hydrogen and CO2, with quite a high negative value of delta G, minus 130. And next we see acetate. Acetate will be split to methane and CO2, and it gives a negative value of minus 32.5 kilojoule per mole of acetate. Now there are some other compounds. These compounds are normally very minor amounts present in anaerobic systems. So most important are hydrogen, CO2 and acetate. And in fact, it has been calculated, and you can find it back in literature, that about 70% of the COD is channeled via acetate to methane, and about 30% of the COD is channeled via hydrogen to methane. Now there were the most important notes on the microbiology that you should recall when we go further in this lecture. So most important is to understand that the anaerobic microbial conversion differs from aerobic conversions. Also, ultimate COD removal inside the reactor proceeds via the production of methane as end product. Methane is a gas. It's very little, it's hardly soluble in liquid, so it bubbles automatically out of the liquid, and that is in fact the COD removal under anaerobic conditions. Under aerobic conditions, do remember, you destruct the COD with oxygen, and COD is gone. Here we in fact recover the COD from the complex compounds that we start with to methane gas as an energy carrier. Another big difference with aerobic technology is anaerobic material, they have a very narrow substrate spectrum. So we do need complex consortia for complete COD removal. And do remember the steps that I mentioned. So hydrolysis, acidogenesis fermentation, acetogenesis, and then finally methanogenesis. Now inside this complex conversion, clearly the acetogenic conversions are most difficult. And they only proceed when we have a centrophy between the hydrogen producers and the hydrogen consumers. And they facilitate this interspecies hydrogen transfer or interspecies electron transfer. Now let's proceed with the COD balance. Do remember the stepwise degradation of complex organic matter into methane and CO2. What happens with the COD? Indeed, nothing. The COD is still there. We only have a conversion on the type of COD. Complex organic matter simplified to very simple compounds, and in the end, all the COD is in methane. A little bit of COD is accumulated in the biomass. But if you do remember, there's little energy available for microbial growth. That means we produce little biomass. So by far, most of the COD is in the end product, methane. Now, I'm sure you remember what is the chemical oxygen demand. But it's good to realize exactly the theoretical definition of chemical oxygen demand. Because knowing that a COD is in fact kept inside the anaerobic system, only transform in one form to another form, we can make very easily a COD balance over the system. And for making a COD balance, we do need to understand very well what is COD. So, as mentioned before, the complex organic matter, which is expressed here in CnHaObND, can be oxidized with oxygen to CO2, water, and ammonium. Now, you see there the numbers 4Na minus 2b minus 3d, and these are related to the average oxidation states of the carbon of the compound that we start with. 4n refers to the carbon, so the amount of electrons that can be released or taken up by carbon. Carbon can donate 4 electrons or can take up 4 electrons. If it takes up 4 electrons, right, then it is completely reduced. And when it donates 4 electrons, then it's completely oxidized. Now the average oxidation states here is 2b plus 3d minus a divided by n. 2b refers to the amount of oxygen molecules linked to the carbon, 3d to the amount of nitrogen atoms linked to the carbon, and minus a to the amount of protons linked to the carbon. If you have oxygen, then already part of the electrons are donated to the oxygen. The same is true for the nitrogen. However, if you only have protons, then the protons, they donate their electron to the carbon. Now this balance between oxygen, nitrogen and hydrogen, if we divide it by the total number of carbon, we can express it as the average oxidation state of the carbon. Now based on the above equation, we can say that 1 mole of organic matter that we just defined, that demands 1/4 times 4n plus A minus 2B minus 3D moles of oxygen. And why 1/4? Well, oxygen can accept 2 electrons, so 1 mole of oxygen gas, O2, can accept 4 electrons. Now if you then multiply this by the weight of the atoms, then we can transform them to A times 4N plus A minus 2B minus 3D grams of oxygen. And that gives us the theoretical COD calculation. So the amount of electrons being transferred divided by the weight of the compound. 12N is the carbon, A is the proton, 16B is oxygen, and 14D is nitrogen. This is the theoretical milligram COD per milligram of organic compound. Now we go to methane production. What will happen during methane production? Well, you know that the oxidation state stays the same. The oxidation state determines, in fact, the carbon fraction that will be reduced to methane or to be oxidized to CO2. The average oxidation state stays the same. We have start with complex organic matter and we end with a mixture of CO2 and CH4. But the oxidation state of the complex organic matter mixture and the mixture of the biogas is the same. So that means that X part of the carbon goes to methane with a carbon oxidation state of -4, and 1 minus X part goes to CO2 with an oxidation state of +4, completely oxidized, and methane completely reduced. Now during the reductive conversion, ammonium and oxygen, they stay completely reduced. Now then we can make an equation. 4x plus 4, 1 minus x is the average oxidation state. Now based on this equation we can isolate x. Now and then we have to realize that during anaerobic digestion this compound is N times X CH4 and N times 1 minus X CO2 plus ammonium. Now since the X is known, it is deduced from the oxidation state, we can fill the X in the CH4 and CO2 equations and we get this formula, which is known as the Busfill formula. This is the anaerobic conversion of organic matter with water to finally methane and CO2 gas. And if the compound is known, you can exactly calculate how much methane and how much CO2 we get. And what you can also see here, it's completely dependent on the average oxidation state of the carbon. Now, we're working with wastewater, so generally we do not know what type of compounds are there. So how we do then address this? Well, we can also assess the quantity of reduced carbon relative to the total carbon, or the demand divided by the total organic carbon ratio, COD divided by TOC ratio. Now the theoretical COD can be calculated with the equation that we just formulated before, and the total organic carbon is in fact the amount of carbon, 12N, divided by the weight of the compound, 12N plus A plus 16B plus 14D. Now if you then this ratio can be then calculated as A divided by 3 plus 2A minus 2B minus 3D divided by 3N. So this is the COD-TOC ratio. From all the known compounds which are listed here, the COD-TOC ratio is plotted. On the y-axis is the amount of methane in the biogas that we produce, and on the x-axis is in fact the COD-TOC ratio, which goes from 0, CO2, to 5.33, which is methane. And this is of course related to the average oxidation state, to the carbon mean oxidation state, which is +4 for CO2 and which is -4 for methane, which is indicated at the top x-axis. All the organic compounds that we know they are on this line, from 0 to the top right to the production of methane. And in fact, so the expected methane percentages in the biogas, you can calculate as 18.75, which is the slope of this line, times the COD-TUC ratio. And COD is a chemical methodology. TUC you also analyze in the lab, and this ratio times the slope of the line will give you the expected methane concentration in the biogas. Now, of course, theory is something else in practice. And in practice, you will see if you then measure the CO2 and the CH4 content, it will be different from the COD-TUC ratio, and there are some for this. The first reasons, well, not all the COD is anaerobically biodegradable. Okay, then part of the, and again, organic matter is also used for cell growth, although not much, but still we have a bacterial yield. Now, and then most important is CO2 is highly soluble in water. Since it dissociates, it reacts with water and it forms bicarbonate. So the solubility of CO2 is much higher than methane, and that's why we have less CO2 in the biogas than we expect, that we calculated, and we have more methane in the biogas than we calculated based on the COD-TUC ratio. So this high solubility influences the CO2-CH4 relation in the biogas, but of course not the methane production. Now, and then there's a subsequent, another very important factor, and that is the possible presence of alternative electron acceptors, anaerobic, sulfate, nitrate, nitrite. Now, if these compounds are present, electrons will be used to reduce these compounds. Sulfate to sulfide, nitrate to nitrogen gas, and nitrite also to nitrogen gas. Now, as in these electrons, they will not go to the carbon. So, if these compounds are present, we'll produce less methane. Now, that can be explained by these oxidation equations given here. On the top part, you see sulfate. Sulfate is completely oxidized, and under anaerobic conditions, it will be reduced to sulfite. Now, the sulfate is 6 plus, 2 minus O4, so it's 6 plus. It will be reduced to S2 minus. So we need 8 electrons. 1 mole of COD is equivalent to 4 electrons. So in fact we need 2 moles of COD to reduce 1 mole of sulfate. Now you can calculate it as well with sulfite, as mentioned here, also with nitrate. And the reaction with nitrate, I guess you do remember, if you are operating an activated sludge plant, when you pursue nitrification and denitrification. You need the COD to denitrify nitrate to nitrogen gas. You can calculate as well here, nitrogen in nitrate is you need 5 electrons to, in fact, to reduce that to nitrogen gas, to the neutral nitrogen gas. Calculate that 1 gram of nitrate requires 0.65 grams of COD, or expressed as nitrate N, 1 gram of nitrate N requires 2.86 grams of COD. And I'm sure you know this number from the activated sludge processes. Now, having explained the different fractions of COD, we can now make a COD balance over an anaerobic reactor. With an anaerobic reactor, we start with the influent COD. This influent COD is converted by anaerobic organisms into its product methane. Now that part is COD in the gas. We also have new sludge growing, and that is COD sludge. And not all the influent COD will be converted, so there will be part of the COD in the effluent. That means the COD influent is equal to the COD effluent plus the COD gas plus the COD in the sludge. And this balance always fit, must fit. That means if you operate an anaerobic plant, you know exactly the amount of COD coming in, you measure the COD in the effluent, and you also measure the COD in the gas, the methane gas, you can in fact calculate how much sludge that you produce. And vice versa. If you don't have the means to measure the biogas, you can, by sludge assessment and the COD effluent, you can in fact calculate how much COD in the gas or how much methane gas you produce. Now, these are gross values, but do realize that in the influent COD, you have soluble COD, you have the solid COD, you have colloidal COD. In the effluent as well, you have soluble organic matter, you have soluble inorganic matter, for instance, hydrogen sulfide. You have solids in there, other dissolved reduced gases. Sometimes methane is also dissolved for a little bit in the effluent. Now, the COD gas is not only methane, but also hydrogen and hydrogen sulfide. These are all reduced gases, and they all contain COD. Now, inside the sludge is the newly grown biomass, but also the entrapped solids. For instance, if you treat sewage, primary sludge will be entrapped into the biomass, and this is also COD of the sludge. Or the fats that are not completely converted, they are attached to the biomass and stay inside the sludge, which is also COD sludge. So it's a little bit more complex than I just explained, but you can, if you do your analysis well, you can make a proper COD balance, and the balance should be closed. Now, to work with it, we do have to remember these conversions, right? I already mentioned from this calculation from 1 mole CH4 to COD. 1 mole of CH4 is equivalent to 2 moles of oxygen. 22.4 liters is equivalent to 64 grams of COD, 1 liter to 2.86 grams COD. Do remember, 1 gram of COD theoretically is 0.35 liters of methane under standard temperature and pressure, 0 degrees Celsius and 1 bar. Now, there's also COD in sludge, and for that we use commonly use molecular formula of heterotrophic biomass, which is C5H7O2. It may differ a little bit under anaerobic conditions, but let's take this theoretical formula for heterotrophic biomass. And we assume the VSS composition is approximated by this formula. Now then we can calculate the mass weight. 1 mole of VSS is then 113 grams. And 1 mole of VSS, we can also express it in COD. So, for one oxidizing 1 mole of biomass, we need 5 moles of oxygen. So, 1 mole of VSS is equivalent to 5 moles of COD. Or 5 moles of COD, 5 times 32 is 160 grams of COD. And that gives us a equation. 1 gram of sludge VSS is equivalent of 160 grams of COD divided by 113 grams of mass is 1.42 grams COD per 1 gram of sludge, based on the trophic biomass. Now, let's then calculate a COD balance. Imagine you are treating municipal sewage and you have a flow of 50,000 cubic meters per day. COD is 500 milligrams per liter, average value. Let's assume a sludge yield of 10%, which is maybe quite a high number, but okay. And we have an efficiency of the COD of the anaerobic reactor of 75%. Now we first have to calculate how much COD is now coming in our reactor. And that can be calculated as 0.5 grams per liter or kilograms per cube times 50,000 cube per day. We can calculate the reactor is loaded with 25,000 kilograms of COD per day. Now what we do know is that the reactor performs at 75% efficiency. That means 25% of this COD is still in the effluent, and that's a value of 6,250 kilograms of COD per day. Now we can calculate how much of the COD goes to the sludge. Now it was assumed that 10% of sludge, converted is 25,000 minus 6,250 times 0.1, 10% of sludge yield, which gives us a value of 1.875 kilograms of sludge COD per day. Or if you then convert it by, if you then divide it by 1.42 COD per kilograms of VSS, we produce 6,320 kilograms of VSS per day. But we now can also calculate how much biogas we're going to produce, which is the influent, 25,000, minus the effluent, 6,250, minus COD to the sludge, 1875 kilograms, is 16,875 kilograms COD per day. Now we multiply this by 0.35 cubic meter of methane per kilogram COD, and we can calculate that this anaerobic reactor will produce about 6,000 cubic meters of methane per day, 5,906. The balance must always fit. Coming back to this presence of alternative electron acceptors, because a compound like sulfate is often present in sewage. Sulfate is commonly used in industry. Think about the fermentation industry. If you have a coastal city, then sulfate may also be part of the intrusion of seawater in the sewer system. That sulfate comes into the anaerobic reactor. So sulfate is a common ion which is also entering the anaerobic reactor. But sulfate takes away electrons and will lower the amount of methane that we produce. So what will happen with the biogas production if you add 200 milligrams per liter or 0.2 kilograms of sulfate per cube to the influent? Do you remember this equation? 1 mole sulfate requires 2 moles of oxygen in the reduction of sulfate to sulfide. So 2 moles of COD is 64 grams. Now what will then happen? Per gram of sulfate, 0.67 grams of COD will be oxidized. And that means in our situation we have 0.2 kilograms of sulfate per cube times 50,000 cubic meter per day is 10,000 kilograms of sulfate is entering the anaerobic reactor, consuming times 0.64 is 7,000 kilograms of CO2 will be consumed. Now this gives 16,875 minus 6,700, 10,000 kilograms methane COD per day produced, which is equivalent to 3,500 cubic meter of methane. So substantially less methane than the previously mentioned 5,900 cubic meter of methane per day, because of the presence of sulfate. Now, the presence of sulfate impacts our anaerobic digester. But there are other factors that are impacting our anaerobic reactor. Now, there are many factors, but let's focus in this lecture series in which we're treating domestic sewage on the most important environmental factors that are also playing a role when you treat municipal sewage. Here we see a list of the various conditions. We will address some of them, not all, some will be discussed in later lecture series. First, temperature and variations, the wastewater strength, presence of suspended solids, the buffer capacity, the pH, presence of alternative electron acceptors, which we just explained, risk of accumulation of inorganic matter like sand, which in municipal sewage is always a problem, risk of formation of scum layers or flotation layers, presence of toxic compounds, other problems. Now these are very important factors that you need to consider when you opt for an anaerobic sewage treatment. Let's go them one by one. First, temperature and variations. As previously mentioned, temperature has a direct impact on the anaerobic conversion. Temperature impacts enzyme activity. In the microbial world, we can differentiate 3 main groups of organisms. We call them psychrophilum organisms with an optimum temperature below 20 degrees, mesophilic organisms with an optimum temperature between 20 and 40 degrees Celsius, and the so-called thermophilic organisms with an optimum temperature beyond 45 degrees Celsius. Now these borders are arbitrary, and of course there are some species in between, etc. But these are the gross, in fact, the gross division that you can make in the temperature dependency. Now then you see here a curve. This curve is generic for any organisms. You have a minimum temperature below which there is no growth. Then you have an optimum temperature where you have the maximum growth. Beyond the optimum temperature, you see that the growth is decreasing. And then you have a maximum temperature where the death rate is higher than the growth rate. Now, depending on the type of a temperature, it will shift. The temperature will shift along the along the x-axis. Now, this curve that can be described by the double Arrhenius equation. In fact, the first part of the curve is the increase in growth, and the second part of the curve is the increase in the death rate. The optimum temperature, then you have a perfect balance, you have the maximum growth of that type of organisms, and when you pass the optimum growth, you have more death occurring. And beyond the maximum temperature, there's no net growth available anymore. Now, temperature, of course, is important, which I mentioned. So the higher the temperature, the higher the conversion rates, and the higher the loading rates. Keep that in mind. Sewage treatment at 30 degrees Celsius is way more efficient than sewage treatment at 15 degrees Celsius. Now, next to temperature, we have the wastewater strengths, and particularly the presence of suspended solids. Now, do remember that the sewage treatment plant, the municipal sewage treatment plant, treats raw sewage. A part of the COD is present as suspended solids. In fact, a very large part, 40 to 50% of the incoming COD is present there of suspended solids. And the stay in the anaerobic reactor behind is primary sludge. And the primary sludge will be digested in the sludge bed of the anaerobic reactor. But the presence of suspended solids, they will reduce the activity. On the left-hand side, you see a schematic representation of the 1 gram of VSS, 1 gram of volatile suspended solids, 1 gram of biomass, which consists only of active bacterial mass. Now, this gives a certain activity of that sludge. Now, in the right-hand graph, you see 1 gram of VSS, but now the VSS consists of active bacterial mass, but also of inert suspended solids. It's all VSS, but only a small fraction is active. Now, the activity of the right-hand sludge is way less than the left-hand sludge. So that means if you accumulate organic inert mass, then we reduce the activity of our biomass. And that happens in a sewage treatment reactor. The more suspended solids are entering the reactor, the lower the activity will be. Now, do remember, under standard operational conditions, you have to withdraw the sludge to keep the sludge concentration at a certain level. So we do talk here about the equilibrium equation of concentrations. Now, if you then look to sewage treatment, what you can see here is a table which is giving the temperature. In the middle column is a wastewater with a very low concentration of suspended solids, so only 5% of the COD are suspended solids. And in the third column, you see a wastewater with 40 to 50% of the suspended solids. The COD is 40-50% of suspended solids. Now, what is expressing here, the numbers are expressing the maximum organic loading rate, the maximum organic volumetric loading rate in kilograms of COD per cubic meter reactor per day. You do immediately see the impact of temperature. The higher the temperature, the higher the loading capacity of our anaerobic system. But there's also a difference between column 2 and column 3. So the more suspended solids, the higher the fraction of the COD that is in the form of suspended solids, lower the applicable volumetric organic loading rate to our anaerobic system. Sewage, we have to deal with the third column. So the loading rates of anaerobic reactors are relatively low. Then buffer capacity and pH. And that is linked to the microbiology that I explained. So inside the anaerobic conversion, we have the stepwise degradation. And one step was a very quick step. And that step is called fermentation or acidogenesis, in which acids are formed from neutral compounds, sugars, proteins, fats. Now, in these acids, they may accumulate. And if they accumulate, then the pH drops. If the pH drops, then the methanogens might be affected, inhibited. So it is very important to understand this and also to understand whether our reactor can an imbalance in this fermentation, preventing that the pH will actually drop. So do we have sufficient buffer capacity in the reactor? Now to understand this, this is the more or less the pH range of the various trophic groups inside our methanogenic biomass: hydrolysis, acidogenesis, acetogenesis, and methanogenesis. Now it is clear from here that the methanogenic organisms, they have a more narrow pH range than the fermentative bacteria. And that means the fermentative organisms, they will be active as well in pH 6, pH 5.5. Meanwhile, the methanogens not. So if the pH drops to that level, we will die off the sludge inside the methanogenic sludge inside the anaerobic reactor. We have to prevent that, so we are dependent on a buffer which is there. Now, if you do remember, how do you calculate a buffer? Well, the pH is equivalent to the pKa value of a compound plus the log ionized form divided by the hydrated form, ionized for the non-ionized form, the acid form. Now, the most important buffer we have is bicarbonate. Now, if you do remember, acetate, 70% of the COD is channeled via acetate to methane. In the end, eventually, acetate is split into methane and bicarbonate. So we do generate our own buffer in the anaerobic system. The bicarbonate carbonic acid buffer has a pKa value of 6.3. And then there's a further dissociation, is a way higher, but for our anaerobic system, the first part is most important. Bicarbonate and carbonic acid. But I just mentioned that acetate splits to methane and bicarbonate. It has to do that we operate our anaerobic reactor under neutral conditions. So the acetate is not present in the form of acetic acid, but is present in the form of ionized acetate. Converting acetate at pH 7 or 7.5 to methane means that we are converting acetate ion, maybe counterbalanced by sodium, to methane and bicarbonate, not to CO2. The bicarbonate reacts with the water, and then we get CO2 plus OH minus. And that means if we're going to digest acetate to methane, the pH will increase. We generate our own buffer by converting acetate to methane. And in fact, you can calculate that. If you digest 500 milligrams sodium acetate, the produced alkalinity is 500 divided by 82. The sodium acetate is 6 millimolar or 6 milliequivalent bicarbonate. So by digesting 500 milligrams of acetate, we produce 6 milliequivalent of bicarbonate. And that bicarbonate acts as a buffer. Now there are other buffers generated during the anaerobic conversion. I informed you about the conversion of proteins. And the proteins, they have ammonium. And this ammonium will also be liberalized during the anaerobic conversion. Now the pH is 7, 7.5, 8. And under these pH conditions, the ammonium will be present as ammonia. So it takes up a proton and a form NH4. Now this water, which is split to donate the proton, it also donates an hydroxyl ion. And this hydroxyl ion reacts with CO2 and forms bicarbonate. And this bicarbonate with the ammonium gives the salt ammonium bicarbonate. That means if we digest proteins, we generate the ammonium. The ammonium binds bicarbonate, and in that way we generate again the buffer, the bicarbonate. We increase, in fact, the bicarbonate buffer. And of course we decrease a little bit the CO2 in the biogas, because the CO2 is now bound with the hydroxyl ion that was liberated in the protonation of ammonia gas. And that is also a metabolism generated alkalinity, which occurs with the digestion of proteins, but also with the hydrolysis of urea. Now, urea is a very important ammonium source in municipal sewage or in fecal matter or whatever. So the ammonium that will be set free binds CO2 to the liquid, increases the alkalinity. Now, if you then assume, for instance, that our sewage has 100 milligrams of proteins, here is glycine with a molecular weight of 89 grams, then that 1 mole is converted to 1.1 mole of ammonium N, and that will bind 1.1 milliequivalent of bicarbonate again. So by knowing the amount of proteins, you can calculate the milliequivalent of bicarbonate that will be bound to the liquid by the released ammonium. And the other one was urea. Also in non-sewage sanitation you will find urea to be converted, but urea under the presence of urease is split into ammonium and CO2. Again, solubilized in water, this gives us ammonium bicarbonate. Now, 1 mole of urea binds an additional CO2 from the biogas, so your pH will go up, and that is also what you observe. When urea is hydrolyzed, the pH will go up, and you will also smell ammonium. 1 mole urea binds 2 moles of bicarbonate, so we generate quite some alkalinity then. There was the buffer capacity, so we do generate our own buffer, particularly with municipal sewage and with black water treatment. Now the other one was the presence of alternative electron acceptors that we also discussed. And that is to do with the S cycle. Sulfate is being reduced to sulfite. Sulfite that can be oxidized again to elemental sulfur. Now there's another part of the electron of the sulfur cycle is the production of organic S compounds. Moreover, if you have reduced sulfite, that reduced sulfite can precipitate, for instance, with heavy metals. Think about iron sulfide, zinc sulfide. So this biological sulfur cycle is very important also for the anaerobic digester. And do remember, sulfate takes away COD to be reduced to sulfite. Now, next to sulfite you also see nitrate, but nitrate commonly is not present in domestic sewage. Nitrate is an oxidized N compound, and in domestic sewage, in the sewage system, we have a reducing environment. So if we have nitrate there, it already will be reduced in the sewage system to the nitrogen gas. So sulfate again is the most important compound here. And there are similarities between carbon and S and sulfur. First, they can appear in the various oxidation states. Carbon -4 to +4, CH4, CO2. Sulfur -2 to +6, H2S sulfide to sulfuric acid. Both difference is 8 electrons. So then they can both act as electron donor and electron acceptor. The end product of the reduced conversion is gaseous, methane, hydrogen sulfide. And they do form precipitates, metal sulfide, calcium carbonate. So they may lead to accumulation of inorganic matter inside the anaerobic reactor. And there's another thing, that sulfur and carbon, they may compete for the same substrate. if sulfate is present, then that sulfate will also be reduced. Now from literature we know that the sulfate reducing bacteria, they have a kinetic advantage over methanogens. And that means sulfate reduction will always occur. As soon as sulfate enters an anaerobic reactor, it will be reduced to sulfite. And that means that next to methane and CO2, we will also produce H2S in CO2. That H2S is a toxic gas, it's corrosive, may attack your boiler system or your burners. So if you do have sulfate in the influent, we have to clean the biogas before it's used as an energy source. And that gives the problems associated with sulfate reduction. First, you have a lower methane yield per organic waste. The biogas needs treatment since you need to remove the H2S. The maintenance costs increase. You have malodor and you have to get rid of the malodor before venting the air. And you will suffer corrosion to engines, boilers, switchboards, reactor parts, pipes, etc. Moreover, the sulfite is also a soluble gas, since hydrogen sulfide, H2S, may dissociate in bisulfite, HS- in the proton. And the pK value of that reaction is also 7.1. That means under neutral conditions, part of the H2S will be solubilized in the effluent. And H2S, HS- is COD. So the post-treatment system requires polishing, requires aeration. And 1 mole of sulfite requires 2 moles of oxygen to be oxidized again. And there's another practical problem. If we have a lot of sulfite in the effluent, then this may cause bulking of the activated sludge process. Since the aerobic sulfite oxidizers, these are the filamentous Ciatrix, leading to bulking activated sludge. So some problems indeed with sulfate being present in the influent. Now there are some other compounds that will impact, of other factors that will impact our anaerobic reactor, but these will be discussed elsewhere in the course that we are now giving. If we think about the accumulation of inorganic matter, think about the sand in anaerobic reactors, risk of scum layers, flotation layers, non-degraded fats and so on, odor problems, and as mentioned, these will be discussed later.